Okay, so let's see if we can generalize these techniques to operations that involve two-dimensional arrays. And we're going to start by looking at matrix vector multiplication. So here what I've written out is a typical matrix vector multiplication with actual numbers. Okay, and how does this work? Well, you may remember that you do this times that plus this times that plus this times that to compute the first element, and then this times that plus this times that plus this times that for the second element. And obviously a better way of thinking about it is to say, oh, the first element is just the dot product of the first row with the vector, the second element is the dot product of the second row with the vector, etc. Interesting. So the dot product that we talked about earlier this week and in previous weeks now comes in as an operation that we encounter when we do matrix vector multiplication. All right, so how else can we think about this? Well, if we take this matrix and sort of arbitrarily partition it like that, then we notice that the result here we can think of as this top matrix times the vector, and this part here is the bottom of the matrix times that vector. Interesting. So when we look at A times X, and we like to think in terms of adding the result of that to Y, one thing we can do is say, take your matrix and partition it into a top part and a bottom part, and look, multiply that times vector X, and then add the result of that to vector Y. And what this here suggests, and what the theory of linear algebra confirms, is that that's just the same as A, the top part of A times X, the bottom part of A times X. But if you then want to add that to vector Y, you need to also identify a top part of Y and a bottom part of Y, because otherwise you can't add these pieces together. So really what we should have done here is said, oh, Y is partitioned in a top part, into a top part and a bottom part, and then the result of this operation is this plus the top part of Y, and the bottom part adds to the bottom part of Y. Okay? Interesting. Now obviously the number of rows that you split off from matrix A must be the same as the number of elements that you split off from Y. Otherwise these things can't be added together. But what do we have here? What we have here is the partitioned matrix expression. If you say this is the original values that were in vector Y. So, ta-da! We have a partitioned matrix expression for matrix vector multiplication. And now all you need to do is take this and use it to derive algorithms, which is what you're supposed to do in this particular unit.